Static forces and torques in robotics. The question that we're going to try to answer in this lecture is how to find the joint forces or torques depending on if we have a prismatic joint or a revolute joint that are required to keep the robotic arm in static equilibrium. Here we have a representative link I, which has an arbitrary shape. This link I would be a part of a series of links that are extending from the base of the robotic arm until the end effector. This robotic arm here, this link I here, has a joint I and a joint I plus 1. Now the forces acting on this link, first of all we have a force from the previous link I minus 1, which is acting at the joint I. We also have a moment. This moment vector is also exerted by the previous link, which is link I plus 1 acting at the same joint. Then we also have the reaction of the force, which is acting from link I on the link that comes after. So this is the reaction of it. This is why we have a negative sign. We also have the reaction of the moment that link I exerts on the next link, which is link I plus 1. So we have the summary here for the designation that we're using. So Fi between brackets represents the force vector. So it's a 3 by 1 matrix, column matrix, Fx, Fy, and Fz. And I, again, it means it's acting on the joint I by link I plus minus 1. And here, this is the force acting on the joint I plus 1 by link I. And the N here is the symbol used for the moment. And we have a similar definition as we have above for the forces. Now, from Newton's second law of motion, and for a case of static equilibrium, if we consider summation of forces acting on link I, so we will have the force vector from the previous link acting on the joint I, and we also have the reaction of the force of link I exerting on the link I plus 1. This is why we have, it's a reaction force, so it's going to be in the opposite direction. This is from Newton's third law of motion. For each action, there's a reaction which is equal in magnitude and opposite in sign. So this is the Newton's second law of motion, where summation of forces is equal to 0. Notice that both force vectors are expressed in the same frame I in this case, in the same coordinate system. Now, usually we would like to express each force in its own frame of reference. And so we want to express the force Fi plus 1 in its own coordinate system. And to do this, we need to multiply it or pre-multiply it by the rotation matrix, which represents the mapping from frame I plus 1 to frame I, and thus keep the whole equation valid, where everything is expressed in the same frame. So if we take these two matrices to the right side of the equation, we will have now the force equilibrium equation. Notice that the weight of the link was neglected. We only considered the forces from the previous link and the force from the link that comes after. And even though it maybe this is new to you, but if you really think about it, it's a very simple problem where you have a link with two forces acting on it. So since it is in static equilibrium, then both of the forces, or these two forces, should be equal in magnitude, as can be seen in the equation here. In a similar way, we have here the summation of moments equal to 0, as a result of the static equilibrium. We're taking summation of moments about the origin of this frame I. So we have the this moment coming from the previous link, the moment coming from the link that comes after, and this force will not create any moment because it intersects with the point I here. So, but we need to consider the moment generated by this force. And a moment of a force is computed using the well-known relationship, the vector cross product of R cross product F. So in this case, R is going to be the position vector from I plus 1 to I cross product the force vector here. The negative sign is moved here, and we will do as we did in the previous slide, where we want to express each moment and each force in its own frame of reference. So instead of having it in frame I would prefer to have it in its own frame of reference, but to do that I need to pre-multiply it or map it by pre-multiplying it by the rotation matrix of I plus 1 with respect to I. As we can see here also for the moment vector, we're going to take these terms to the right side of the equation. And one thing is to notice that these two matrices, the multiplication of these two matrices is going to be equal to the force Fi, as we obtained from the force equilibrium equation in the previous slide. So now we have the moment equilibrium equation. On one side we have the moment at the joint I, moment vector at joint I. So this is a column matrix nx, ny, and nz at the origin of frame I expressed in frame I. And here we have the rotation matrix. This is the moment acting on the next link, and this is the position vector, and this is the force acting at the origin of frame I. Consider a revolute joint. If I'm talking about the actuator torque, so this is the component of the moment vector that is not resisted by the structure itself, because we know if this joint was a revolute joint, from the definition of a joint, it should allow a rotation about the z-axis. But in order to keep it in static equilibrium, that means that the torque attached to this joint should be able to exert a torque equal to the moment acting at the joint itself. So this is why, but it should be opposite in magnitude. So this is why we have a negative sign here, and this is the moment vector, and this is a dot product. So why are we doing this dot product with these with the unit vector in the z direction? Because this way we can extract the component in the z direction. So it's a matrix approach, matrix algebra approach in order to extract one component from a certain vector, which is the dot product, which is equivalent again also to a projection on a certain axis. And dot product in matrix algebra transforms into taking the transpose of the first vector and multiplying it by the second vector. So the second vector was kept as is, but the first vector was transposed. So instead of being a column matrix, now it's a row matrix. So this becomes like a 1 by 3 matrix. This is a 3 by 1. So the result is going to be a scalar quantity, which is the value for the, in this case, going to be the value for the torque at the joint in order to keep this link in static equilibrium. If it was a prismatic joint, so then the joint itself is supposed to allow motion along the z-axis, a translation along this axis, and in this case, if you want to keep it the link in a static equilibrium, so the actuator force should be equal to the component of force in this direction at this joint, the origin of this frame. And this can be again represented in a matrix form by the dot product, where we have now the transpose of the first vector times the other vector, which has the unit vector in the z direction. And this will give me also a scalar quantity, which is the value of the required joint torque. So these are the equations or the formulas that we're going to use in our solution in the next slides. Here we have an example where we consider a planar 2 degrees of freedom robotic arm. We have two joints, both of them are revolute joints, represented by theta 1 and theta 2. And we are required to calculate the static torques required for each joint motor. We will supposedly have one motor here and another servo motor, and we want to know the magnitude of the torque required to keep each of these two links in static equilibrium, and assume that the end effector is subjected to a planar force vector F. So this force vector has only components in the x and y and no component in the z axis. So this is the external force F, and this is beta, the angle it makes with x3. So the way we are going to proceed with this example is that we'll have one box here on the right that includes the required formulas. This is for the force equilibrium, this is the moment equilibrium, this is for the revolute joint. If it's a revolute joint, this is going to be the torque, and if it's a prismatic joint, this is going to be the value of the force. And this is the formula for the skew symmetric matrix. These are the R rotation matrices 1 to 0, 2 to 1, and 3 to 2. We already have explained how to obtain these in the previous lectures. And this is the position vector of origin of frame 1 with respect to 0. This is 2 to 1, and this is 3 to 2. So we're going to start with I equal 2, where 2 now is the number of joints, maximum number of joints we have in this example. So if you substitute for I2 here, so it becomes F2, R2 to 1, R3 to 2, and F3. So we have this here, and R3 to 2. So we will get it here from the extracted matrix here that we extracted it before from the transformation matrix. So this is the identity matrix. We have it here. And F3 is the force vector acting at the end effector expressed in frame 3. And we can see that it will have one component in the x3 direction, which is F cosine beta, and we have a component in the y direction if it's F sine beta, and no component in the z direction. So if you multiply this vector now by the identity matrix, it will just gonna be the same vector here. Now so I added one more box, a green one here, where I have the results. So I'll keep updating this with the new results as we proceed. So now, we have the force acting at joint 2, and we will see since both frames, frame 2 and frame 3 are parallel, so I expect that the force will have the same components as in frame 3. So it's going to be the same. Now what about the moment? So I have to find the moment the moment acting here at joint 2. I need to substitute I2 into this formula where I'll have N2 R3 to 2 N3 and P3 to 2 multiplied by F2. So we already have F2 from the previous slide, position of 3 to 2, we have it here. It's which is really 3 to 2, think about it, it's a translation in the x direction by an amount of L2. So this is why L2 0 0. And for the N3, yeah, what's N3? N3 is the moment acting on the end effector, and we were told nothing about this in the example, so we'll assume that there's no external moment acting at the end on the end effector. This is why it's zeros, and R3 to 2 it has the value shown here, which is the identity matrix. So if you multiplying it by 0, this is a 0 here, identity matrix by 0, still gonna give me the 0 column matrix. And what about this cross product here? So the cross product, we know that a cross product represented in matrix algebra is going to be simply the first vector expressed in a skew symmetric matrix multiplied by the second vector. So you keep the second vector as it is, but the first vector you have to write it down as a skew symmetric matrix. So and this is the formula for a skew symmetric matrix. So if we have a vector A, so this is the AX component, AY component, AZ component, it's skew symmetric. So and this here we have only in the X component, so I only substitute in here and here. So we'll have minus L2 and L2. And if you multiply these two matrices, the first row is going to give me a 0, second row is also going to give me a 0, third row is going to give me L2 times F times sine beta. So now I have the moment about joint 2. And so if you really put them together, what we are having here is as if we are moving the force vector to here. But we know that when you move a force vector, you change its line of action, you have also to compensate with a moment. And this moment is computed by taking the projection, the component of F, which is along the y-axis, which is now perpendicular to this distance. So I take this perpendicular component and multiply it by the distance L2, and so I have F times sine beta times L2. So this is the moment about this joint. So now we have the force acting at joint 2 and we have the moment acting at joint 2. Now we need to compute the static torque required at joint 2 in order to keep link 2 in static equilibrium. And this is obviously, since the torque here exerted by the motor should be about the z-axis, so it makes sense that it should be equal in magnitude to the component of the moment acting at joint 2. So it should be equal to this, but opposite in direction in order to accomplish the equilibrium condition. And this can be represented as a matrix multiplication, we said before, as a dot product between the two vectors. And the dot product again can be expressed as the transpose of the first vector times the second vector. And so this column vector now should be transposed into a row matrix. So I have 0, 0, L2, F sine beta, and multiplying it by 0, 0, 1, a unit vector in the z direction. So obviously the result is going to be minus L2F sine beta. So you can see that we updated the results section here So we have the force, the moment, and the required static torque at joint 2. Now we're going to proceed with I equal to 1, and so when you substitute for the force vector with I1 here, F1, R21, and F2. So R21 is found here, so we bring it here, and F2 we already found previously in the previous slides. So we have the force at joint 2, and it's just a matter of matrix multiplication, cosine 2, which is cosine theta 2 times F cosine beta, minus sine theta 2 times F sine beta, plus 0 times 0. This will give me the first row here, first element, I mean. The second element is obtained by multiplying this row by this column in the same way, and the last one is going to be 0, last element is 0. So there is a trigonometric identity that tells us that cosine beta cosine theta 2 minus sine beta sine theta 2 is going to be equal to cosine of the summation of these two angles, beta and theta 2. And we have a similar also trigonometric identity for where we have cosine sine, sine cosine, and it's going to be sine beta plus theta 2. So now this is the force acting at joint 1 here. So it also makes sense if you think about it. We have the this force vector moved here, and we have both of its components now in this coordinate system. This is why we have the components, not only beta, but we have also include theta 2. So cosine beta and theta 2, we added them together because both of them are about the z-axis. So we updated the results section to include now also the force. We're going to proceed with computing the moment by substituting I equals 1 into the moment formula. So it becomes N1 R21 into position of frame 2 and the force acting at frame 1. So you can see R21 is already given here. We have it here. N2 was computed previously, and plus L1, the P21, also we have it, the position of frame 2 with respect to frame 1. We bring it here, and F1 was previously computed to be as follows. So now we just do the matrix multiplication. This is going to be a 0. This row by this column is going to be give me a 0, and this one is going to give me this element here. Plus, now we have the cross product. We said before that cross product can be represented by taking the first vector, writing it in a skew symmetric matrix, multiplying it by the second vector. So L1 instead of AX here. And then if you multiply these two matrices, this is gonna give you this vector. Add them together, and this is gonna be the moment matrix at joint 1. So now, if you look at the results section, we have updated it with the moment at joint 1. Now we just need to compute the required torque at joint 1, and this is going to be equal to this magnitude, but multiplied by -1, as you can see. And we can also do it as the transpose of the moment vector times the column matrix 0, 0, 1, which represents the unit vector along the z-axis. And we'll get the same result, of course. Here we see that we have all of the results now. We have the force, moment, and the torque at joint 1 and at joint 2, also at joint 1. You want to maybe write joint 1 rewrite it in a different way. So I want to just have the force cosine beta as a common factor and the force sine beta as a common factor here. So first of all, I need to expand sine of the summation of two angles and to have it now as the sine of the first angle, cosine the second, plus the cosine of the first angle, sine of the second, but we have a negative sign here, and both of them gonna be multiplied by L1 and F. And now we group them together, group the terms that have cosine beta. We have only one term that has cosine beta here. So we'll have F cosine beta multiplied by minus L1 sine 2. And here we have the two terms that have sine beta. So we will have minus L2 and minus L1 cosine 2. And so this is a new way to write the torque at joint 1. Nothing changed. The result, the final result, going to be the same, but we just want to write it in a different way. And this is for torque 2 as before. We didn't change anything. Now we want to bring these two equations and write them in one matrix equation. So we have the column matrix of tau 1, tau 2, and you can see now this matrix equation is equivalent to these two equations. So because if you multiply L1 sine 2 by F cosine beta plus L1 cosine 2 plus L2 times F sine beta, this is going to give me this same equation here. And if you multiply 0 by this and L2 by this one, don't forget the minus sign. This is going to give you your second equation. So this is another way of writing down the torques at joints 1 and 2. Now we have them in a matrix form. That's it, not much here, just writing it in a more compact way. So this is the result from the previous slide. I want you to compare this with this relationship. This one we got it from a previous lecture, the one about the Jacobian matrix, where we have the linear velocity of the end effector as a function of the joint rates. So this was the Jacobian matrix, or if you want, you can call it the Cartesian part of the Jacobian matrix, JV. If you compare this one here with this matrix here, what do you see? You would simply see that this matrix is basically the transpose of the Jacobian matrix. L1 sine 2 comes here, this element comes here, the 0 comes here, and L2 comes here. So you can simply say that the torque, static torque, joint torques, vector or column matrix is going to be equal to minus the Jacobian matrix, or the transpose of the Jacobian matrix multiplied by the force vector at the end effector, because F3 expressed in 3 and consists of what? The force times cosine beta, which is the expressed in the which is projected along x3, which means expressed in frame 3, and this is also here we have F sine beta, which is the projection of the force along the y direction, which means expressed in frame 3. So, and this is a very useful conclusion. So instead of going through all of the procedure, we could immediately just substitute in the Jacobian that we are supposed to have already found it in our linear analysis or the kinematic analysis of the robotic arm. So this would have been already obtained. So I just take the transpose of it and multiply it by the force vector of the end effector expressed in its own frame to get the required joints. And this turns out to be a general rule for robotic arms. So we can say that the column matrix of the static joint torques or actuator forces is going to be equal to minus the Jacobian matrix multiplied the transpose of the Jacobian matrix multiplied by the end effector force expressed in its own frame. This other J, this is a typo, so forget about this one. So I want you to try something now. What if we want to try to multiply the transpose of the Jacobian, but this time expressed in the base frame, and multiplied by the force vector at the end effector, but again expressed in the base frame? What would we get? So you have to go back to the Jacobian matrix lecture, where we have the linear velocities in the base frame, from which we can extract the Jacobian expressed in the base frame. Here we have it here now. The force of the end effector expressed in the base frame, for our case, it's going to be simple. So this F, now you want to find its projections on x0 and on y0 instead of its projections on x3 and y3. And the projection of F on x0 is going to be, then in this case, F times cosine of beta plus theta 2 plus theta 1, and the projection of it on y0 is going to be F sine beta theta 2 and theta 1, as we can see here. So if we multiply these two, the Jacobian matrix by this force vector, we are going to have this this relationship here. Maybe we need to simplify it in the next slide. So I'm gonna leave it to you to read through this slide. You can pause it and look through the mathematics here. It's straightforward. We're gonna do matrix multiplication, and then we're gonna use some trigonometric identities to expand the cosine of a summation of angles and the sine of a summation of angles, and we will rearrange the terms, and finally after some terms will cancel out with each other, and we will end up with this simpler form here. So we can see that interestingly, the multiplication of the Jacobian matrix by the force vector, when both of them expressed in the base frame, it's gonna be the same as the result we got before, where we had the Jacobian matrix expressed in frame 3 in the end effector frame. And this is an important conclusion. This means that we have two options for finding the joint torques, static torques or static forces, and either by pre-multiplying the force vector in the end, acting at the end effector and expressed in the end effector by the Jacobian matrix, by the transpose of the Jacobian matrix expressed in the end effector frame, or alternatively we can write it down and find it by pre-multiplying the force vector at the end effector expressed in the base frame by pre-multiplying it by the transpose of the Jacobian matrix expressed in the base frame. So the question would be now, which one would be easier to use? Should I use this one or should I use this one? Okay, so I will tell you something. If F is constant in frame 0, so if this force will have constant in magnitude and direction in frame 0, and for example, in the case if we're talking about the weight of the payload, so this is the end effector, it will be carrying a Sison payload. So in that case, the weight will always be, it will be constant in magnitude, and it will be always pointing toward the negative y0. So it's constant with respect to the base frame. In that case, it's easier to use this formula, where everything is expressed in terms of the base frame. Otherwise, if the force vector here is constant with respect to the end effector, it would be easier to use this formula. So here we have the same problem as before, the same example, but this time the force acting at the end effector is the weight of the payload, W. So as I explained in the previous slide, it will be easier to use the formula for the static torque, but this time expressed in the base frame. So we already have the Jacobian. We should have already computed this in from the previous lectures, considering the kinematics of the robotic arm. But we need to find its transpose, and the transpose is easy. Every row becomes a column. First row becomes the first column, second row becomes the second column, and within the base frame, the components of this W is going to be 0 in the X and minus W minus the weight in the Y direction. So you can see it's straightforward. Now you multiply these two matrices, row by column, to get the magnitude of the torque at joint 1 and the magnitude of the required static torque at joint 2. Now, just for extra explanation, or for giving extra, let's say, verification, we cannot try to solve it again, but this time with the formula where we have everything expressed in the end effector frame. You will see that's going to be a bit more difficult than this case, but just to make sure that you understand how it is done. Here we're going to solve this, this time everything in the end effector frame. So this is the Jacobian from the end effector case expressed in the end effector frame. We're going to take the transpose of it. This row becomes a column, this row becomes a column. But what about the force? Now the force should be expressed in frame 3. So this W should be expressed in with respect, so we'll have the component in the X and component in the Y, but the X, which X? X3. So then W of cosine beta is projection on X3, and W sine beta is its projection on Y3. However, beta from a geometrical relationship will turn out to be 270 minus the summation of theta 1 and theta 2. It's easier for you to understand if you look at this small angle here. This small angle here will be what? Will be theta 1 plus theta 2 minus 90. So theta 1 plus theta 2 minus 90 will give me this one, which is the same as this angle. Then if you want to find beta, beta will be 180 minus the theta 1 plus theta 2 minus 90, which is going to give me 270 minus the summation of theta 1, theta 2. So if you substitute this into here, this becomes your column force vector, or column matrix. And we can write down sine theta 1 plus theta 2 as we did before in previous lectures as sine 1, 2. Same thing for the cosine. Now we multiply these two matrices, and after you do the multiplication, you would also need to rearrange the terms in such a way as you can simplify it a bit, because you can see here, for example, we have the identity, the trigonometric identity, where we have cosine, cosine plus sine, sine. This is going to be cosine of the first one minus the second angle. So it becomes cosine of theta 1 plus 2 minus theta 2 becomes cosine theta 1. And this is the same result as the one we obtained in the previous slide. Same thing for tau 2. So you can see that it's a bit a little bit more complicated when considering the formula in the end effector frame. So anyhow, regardless of which approach did we use, this would be the joint static torque at joint 1, and this is the static torque at joint 2. And the result here can be useful in selecting the motors at these two joints. So, and this can be done by considering the maximum values that can be obtained for these two cases, for these two torques. And the maximum value depend on the variables here. So the variable is going to be cosine theta 1 and cosine of the summation of theta 1 and theta 2. And we know that the cosine in general have extreme values of -1 and 1. So we can think of a maximum value of 1 for each one of them. So, and when would this be 1, and when would this one be equal to 1? In reality, the cosine is going to be equal to 1 when the argument or the angle is equal to 0. And so this corresponds to the case where we have theta 1 equal to 0 and theta 2 equals 0. And this is the case where the robotic arm will be fully extended and horizontal. Think about it. Theta 1 is 0, theta 2 is 0. This will only happen when the robotic arm is fully extended and in the horizontal position. And in that case, we take this is going to be 1, this is going to be 1, and tau max will be L1 plus L2 times W. And tau 2 max is going to be L2 times W. And so the values here can be used for the motor selection. So a motor should be capable at least of handling these static torques. And if you really think about it, you will see that we did a lot of calculations here, but basically we could have determined these torques by inspection, by thinking about this simple configuration and what would be the maximum torques at each joint. You can recognize by inspection that the maximum torque case would be when the robotic arm is fully extended and horizontal, and just in that case immediately you can decide that the torques required, maximum torques, will be L1 plus L2 times W for torque 1, and for torque 2 is going to be L2 times W. However, the procedure that we established in this lecture would be valid for any other robotic arm, regardless on the level of complexity, on the number of joints, or the type of joints. That's it for today, and thank you. This is another example to show you how easy it is to compute the static torque and or static torques or forces for a robotic arm using the Jacobian. In this example, we have 2 degrees of freedom revolute prismatic robotic arm, and we need to calculate the static torque at joint 1 and the static force at joint 2 in order to keep this robotic arm in equilibrium. So the equation that we're going to use here is has minus the transpose of the Jacobian expressed in frame 3 times the external force acting at the end effector, which is frame 3. So this is the Jacobian as we found in a previous lecture, and these are the components of the force F. So we can see that the external force F makes an angle of beta with the x3, and thus we'd have 2 components, one on x and one on the z axis. And since the whole thing is planar and the force itself is planar also, so we'll have no component on the y direction. We take the transpose of the Jacobian, so each row becomes a column, as we can see here. We multiply these 2 matrices, and this is going to give me a value for the torque at joint 1 to be equal to minus d2 plus L2 times F times cosine beta, and the force static force required at joint 2 should be minus F times sine beta. So that's it, straightforward.